This is problem 4-10E. It's on page 232. Figure P410 shows a stepped shaft in torsion. The larger section also has a hole drilled through it. Compute the maximum shear stress at the step for an applied torque of 7,500 inch-pounds. And then B, determine the largest hole that could be drilled in the shaft and still maintain the step near the hole at or below that at the step. Okay, so for part A, we want to compute the maximum shear stress at the step for the applied torque. Now the applied torque, T, was 7,500 inch-pounds. Okay, now is this pounds force or pounds mass? When there's no subscript, it's force. Okay, so how are we going to do this? How are we going to compute the maximum stress? Well, the maximum stress is going to be TC over J, where C is the outside radius, right? Except for one thing. We've got stress concentration, so this is just the nominal amount. So we'll need a stress concentration factor. Does that make sense? To get the maximum stress. Okay, so it doesn't really matter what we do first, so why don't we go and get the stress concentration factor first. We'll go to the appendices, see what we can find. Got the stress concentration factors marked. And let's see, it looks to me like this would be page 730, A22-7. So what do we need in order to get the stress concentration factor? Well, let's see, we need R over the diameter. It says D sub G, but I think that's a misprint. I think D sub G is the diameter of a groove. What they really mean is just lowercase d. So R over D is what we need for the x-axis. And so R is the fillet radius on the step, and that's 0.08 inches. The diameter of the smaller section is 1.5 inches. Both of these are inches. So if you would, calculate that for me. It's basically 8 over 150. That's how much?
.053.
1053?
.053.
I was going to say. No way there'd be a 1 there. So 0.053. And then to figure out which curve we're on, we need to take the larger diameter over the smaller diameter. And the larger diameter was 2 inches. So 2 over 1.5. I should be able to do that in my head, but I can't seem to think. It's 4/3. I should know 4/3. What is 1.25? 1.3, that's right. 1.33 repeat. So what stress concentration factor should we use? Well, let's go to the x-axis, 0.05, 0.053 really. And the diameter ratio, let's see, I see a curve for 1.25 and it's close to a curve for 1.67. So I'll just do my best and go in between the two. Take my best guesstimate. So each division is 0.01. So yeah, I do need to be close to the line for 0.05. And my best guess is 1.6. What do you guys think? Does that seem reasonable? I hear a lot of silence. Okay. Let's make sure everybody on the front row sees how I got that. You understand it? Oh, can't see? All right. Well, the stress concentration factor I got from these, K, is 1.6. So let me start at this end. Once I show you where I got it from, then we'll turn around. You guys aren't following. Sorry. Let's see. So you see how I got it? Yeah. Okay. All right. Make sure the people around you and behind you.
So the calculator is 1.33.
Right.
And you come over to 0.5 here. Right. That's your calculator. Right.
So,
The 1.25. On that line.
What I really did is if I go up on the 1.5 line, I need to go a little above 1.25, and I need to go a little over.
Okay.
So that 1.6 is you guys have it? Make sure the people behind you understand it. You guys have it now?
Usually 053, this measurement, and then the 133 line.
Right. The closest. Make sure the people behind you understand it.
Okay, so he took what's right here, R over G, and then you got that number, and you went down there and
Anyone struggling with it, need help?
diet, big D over little d, which was.
As soon as you understand it, make sure you turn around to the people behind you and make sure they understand it. You're out of people on the back.
So, yeah, he chose that. You
You can make sure the geese understand it outside. That's gonna take a while.
He could have chose like 1.55 here, just made that big, so we found
And if you're watching the video, you should make sure you know how to find this as well. It's on page 730. Anybody disagree and think it shouldn't be 1.6? Now, would you be wrong to say that the value is, let's see, would you be wrong to say the value is 1.65? That may be a little too much, right? Because that's at the next curve at 1.67. So that's probably a little too much. Could you say it's 1.61? Sure. What difference does it make? Right? So this is about, and you'll see me use this symbology a lot. I'll put a tilde above it to mean approximately equal to. So there's our stress concentration factor. Well, what else do we need? Well, we need the outer radius. That's no big deal. Well, we have to be a little bit careful. Which outer radius? The smaller one or the larger one? Look again at page 730. And you'll notice that the nominal stress is calculated based on the smaller diameter. Do you see that? In fact, do you recognize that pi d cubed over 16? I still don't remember the name of it.
The polar section
Not,
modulus?
yeah, polar section modulus. See, you guys have already got it. All I remember is the polar moment of inertia is J. So I've got to get used to using this terminology. But yeah, you see the polar section modulus appear as a part of the nominal stress. So this is based on the smaller radius. All right. So let's see. Yeah, in fact, let's think about this. Would the largest stress be in the larger diameter member and the smaller diameter member? I mean, at first it's a little confusing because the larger diameter member has the larger value of C. But if we combine these together so that we have, what is that, the polar section modulus? I can cheat and read the slides for right now. If we combine them, we know that the polar section modulus is just pi d cubed over 16. Now, if we use the larger diameter here, that's actually going to decrease the stress, right? Because it's inversely proportional. The stress is inversely proportional to the cube of the diameter. Does that make sense? So it makes sense that the highest stress would be in the smallest section because the smallest section has the smallest diameter once we combine these two together. So I can see why they're concentrating on the smaller section. Does that make sense? All right, so let's continue with the smaller section. All right, in fact, I think we've got pretty much everything we need here in order to calculate the stress. That's what we're asked to find, right? Yeah, maximum stress at the step. Okay, so let's see, 1.6, the torque was 7,500 inch-pound force. I'll make that clear by putting the F on it. I'm going to put the 16 up here from the denominator of the denominator, and then pi goes here, and then D, this would be the diameter of the smaller section, and that is 1.5 inches. that has to be cubed. Okay? Notice what happens. We'll get PSI out of this because one of the inches will cancel. We'll have pounds force per inch squared. So please plug that into your calculator. 1.6 times 7,500 times 16 over pi over 1.5 cubed. Let's see what you get. Tell you what, I'm going to get rid of some of this so we can reclaim some board space while you're calculating. This is part A. I expect about 37,000 or so. May not have done that right in my head, but that's what I'm thinking.
18,000.
How much?
I only got 18,000.
18,000?
I got 18,000.
Okay, well, I'm not thinking right then. 18,000 exact?
No, 18,108.3,
108, okay.
if you want to get that far.
Nah. This is more than we need. So do I have anyone seconding that one? Agree? Yeah. All right, good. So there's the stress. I must have had a factor of 2 in there somewhere that I was not counting for. There's the maximum stress, and it occurs in the smaller section around the step in the shaft. Now, part B asks the question, determine the largest hole that could be drilled in the shaft and still maintain the stress near the hole at or below that of the step. So in other words, near the hole, we're going to go ahead and say that the stress is just 18,000. I guess we can use the 108 if we wanted to, PSI. Okay? And so the question is, what's the largest hole we could drill? Well, how could we solve this? Well, think about it with me. This stress is going to be equal to the stress concentration factor around the hole. Let me just write hole here to differentiate because it's going to be different, right? Multiplied by the torque over the polar section modulus for part B. That's going to be different, right? The polar section modulus for part B is still going to use the same equation. It's still going to be, what was it, pi d cubed over 16, I think?
Small.
Right, but now we're in part B, so we're in the larger part of the shaft, and so now it is the larger D. That's why it's different. Good point that you're noticing. That's good. Okay. So I think what we can do is just say, well, this is KT, and let me drop the whole. Understand that this is part B. Okay, so that's different also. Times the torque divided by, and let's just plug this in, pi d cubed, and then 16 up here. Okay. Now really, the question of the size of the hole is more a question of what's the stress concentration factor, right? So let's rearrange the equation and solve for the stress concentration factor. So that would, see, this is getting messy. Let's do it here. So if we want to solve for this, then what we'd have is the stress concentration factor for part B of the problem is the maximum shear multiplied by pi d cubed divided by 16t, where t is the torque. Let me move this a little bit. Okay? You see what I did? All I did is I rearranged and solved for the stress concentration factor. Okay? Questions, comments? You doing okay? Thanks. Okay, so the stress concentration factor for this part, I'll just drop the B subscript, we know we're talking about something different now, is 18,008 psi multiplied by pi, multiplied by the diameter cubed. But the diameter in this section, let's see, it was 2 inches, wasn't it? Yeah, 2 inches. So 2 inches cubed divided by 16 and divided by the torque, which is 7,500 inch pounds. Okay, so if we have PSI, the pounds here will cancel with these pounds. Pounds per square inch, the square inches will cancel with 2. These will be left with inches in the numerator, inches in the denominator. Do you see how all of the inches cancel? And we get something that's non-dimensional, which is what we should have for stress concentration factor. Okay, so again, I need calculator help. 18,108 times pi times 8, because 2 cubed is 8, divided by 16, divided by 7,500.
I got 3.79.
3.79. Anyone else agree with that? Second? Okay. So we're looking for a stress concentration factor of almost 4 around the hole. So let's see. Here we go. Page 728. So the curve we want to look at is curve C. Now on the x-axis we've got a diameter ratio, so we've got to figure that out first. The diameter ratio is the smaller diameter to the larger diameter. That's 1.5 inches over 2, which is 0.75 if I'm thinking right. Yeah. So on the x-axis would be at 0.75, so that's all the way on the right-hand side of this chart, all the way at the limit. And then if we try to go up to curve C, we notice that it doesn't intersect. Okay, so let's see. Oh, but we've got to be careful here because KTG is based on the nominal section in a round bar without a hole. So that's going to throw a monkey wrench into things. Let me see if I can figure out what that means. Well, that's going to affect a lot of things because the, no, it shouldn't affect that. Let me think for a minute. That's fine. I'll have to think about what this means. Because the problem I've got is that curve C does not intersect. Oh, I'm being dumb here. Do you guys see what I'm doing wrong? What's that?
You're using the small diameter.
That's right. We're trying to find that this diameter is not the diameter of the step in the shaft. I went back and I'm thinking about the step in the shaft. That diameter has to do with the diameter of the hole, which is what we're looking for. Okay? So I can't do this. This doesn't make any sense. This is for the step. This is not for the hole. See what I did wrong? So I was confused because I looked at this and thought small diameter. That should be the diameter of the hole. So instead what we should do, go to a stress concentration factor on the hole of 3.79. So that's pretty arrogant, right? And we can read off 3, 3.5, and 4 pretty easily, but whereas about 3.8. And then go over to curve C, and here we're going to have to really guess. It looks like that ends up pretty much at the lowest point on the curve. And so this is really reaching, but my best estimate of the diameter of the hole to the diameter of the larger section of the shaft is very approximately 0.1. Do you guys see that? It's about the best I can do here. Okay. So what does that mean? Well, that means the diameter of the hole would be about 1/10 of the diameter of the shaft, so that's what, 0.2 inches? That would be the maximum diameter of the hole. If it's any bigger than that, then we'd have to have a larger stress concentration factor. All right, so 1/10 of 2 inches is 0.2 inches. Make sense? Any questions? Yes?
I'm confused as to where you got the tall max piping.
This
No, down there.
down here?
Yes.
Where did this tall max come from? That was a problem in the problem statement. It says in part B, if you want to keep the stress, the maximum stress, about the same in the larger section around the hole that's drilled in it, the transverse hole, as it was in part A, then what size does the hole have to be? So how did I get this number? I used it from part A because they told me to.
Okay.
Does that answer?
This looks like it just got stuck in there. With the previous.
Here, oh, I'm rearranging. See, I've got tall max over here, And I guess what's confusing you is I didn't write it here as well. Tall max is basically T over the polar section modulus, but we need the stress concentration factor. And so all I'm doing here is rearranging and solving for the stress concentration factor. Does that make sense?
Yeah.
Good question. Anybody else? Or anything else? Is that clear for everybody now? Perfect.